It'll take me a few minutes to get mic'd up here. All right. All right. So I have to say, this is one of the biggest audiences that I've ever spoken to, and certainly one of the most diverse. So I'm really excited to be here, and I hope you guys enjoy what I have to talk about. So, like Meg said, thank you, Meg and Jay, I'm going to talk to you tonight about the brain and actually how it allows us to remember not only our past, but our futures. But before I get into what the brain does, I think we really need to think about what memory is. So, I think memory is actually many things, and as scientists, one of our jobs is actually to define what we're actually going to research. So, one thing that we might think of memory is the things that we know. So, for instance, you might know that George Washington is the first president of the United States, or you might be able to remember the Pythagorean theorem, right? That a squared plus b squared equals c squared. You might remember the rules to your favorite board game, for instance, or you might know that an avocado is a fruit just like a strawberry and an orange. So those are all different kind of factual knowledge that we acquire across our lifetime, and that certainly is one form of memory that we have. Yeah, I think so. Better? Yes? No? I can try and put it more towards the center. Is that better? Okay, awesome. All right. So we can also think of memory as the things that we know how to do, right? So you might know how to ride a bike or drive a car. You might know how to use a video game controller to do all the things you need to do in your favorite video game. Or you might need to know how to do a different athletic kind of ability, gymnastics, or in this example, how to throw a free throw. And so we can think of all of these kind of things as memories as well. So the skills that you learn are actually different forms of memory. And yet there's other kinds of things. We can think of these as automatic responses, or what is known in science as conditioned responses. So how many here have heard of Pavlov and his dog? So a few of you. So Pavlov is a very famous scientist around the turn of the 20th century, and he actually did this experiment where he had dogs in his laboratory, and he rang a bell, and then he gave his dog some food, and of course the dog salivated, right, when he got this little treat. And after many times doing this, bell, treat, the dog, of course, learned that the treat was predicted by the bell, and instead of salivating to the food, right, the dog learned to salivate to the bell, right? So it's kind of this conditioned reaction. Bell rings, I salivate in anticipation of the food, right? So it's kind of a habit, right, we acquire. But you can also think of all the fears that you might have, phobias that you might have, fear of snakes, fear of small constricted spaces, for instance. Those are actually also different forms of memories, these kind of habits or fears we might acquire during our lifetime. So it turns out memory is many things. And as scientists, it's important to be able to characterize and think about these different aspects of memory, because what we now know is that all of these different things that I've described to you are actually supported by different parts of the brain. And the kind of memory that I'm going to talk about today, I think, is what we most stereotypically as individuals think of memory. So the events or the individual experiences that we have across our life. So these can be as simple as, I can ask you, what did you have for breakfast on Monday? Right? Or I might ask you where you left your keys last night, or, for instance, where you parked your car for this event. Right? Or they can be more memorable things, like remembering who your first kiss was with, or where you were at, or remembering potentially your first day of school, or maybe your wedding. Right? So those are all individual events. They're unique. They only happen to us once. Right? We might park our car multiple times, but we park our cars in different places every time. So these are really unique memories. And so what makes these kind of memories different than all the rest that I've described to you, right, the facts, right, the skills, right, the habits and fears, right, remembering an event is a form of mental time travel, right? We can think of this as, you know, we can all be Dr. Who's and our TARDIS, and we can, when we think about our first kiss, we actually transport ourselves to a very specific place and a very specific time with a very specific person, right? So we can think about this as projecting ourselves back into the past. And so the part of the brain that I'm going to focus on in my talk we can think about as our TARDIS, like our time machine that we have in our head. And it's a structure in our brain that's called the hippocampus. And I'm going to apologize, because there are two screens. I'm not going to know all the time what to point at. So this hippocampus here is in pink, or this magenta color. It's a structure deep in the middle of our brains that's very essential to our ability to both form and recall these specific event memories that we have. And so what I'm going to show to you now is actually a video of an experiment done in a human person that's recording from an individual brain cell, a neuron, in this particular part of the brain. And you think, wow, can we really go stick electrodes into people's brains? Well, not usually, but these experiments happen to be done in clinical patients, most typically those with epilepsy, who are coming into the clinic to have some pre-surgical recordings done from their brain to determine where their seizures are actually coming from before they have surgery to go in and take out the damaged tissue. Now, scientists like myself take advantage of this, and we actually have these people do tasks while they have these electrodes embedded in their brains so that we can actually see what these individual cells actually do. And so in this particular experiment, the gentleman, we'll see it first, he's going to be shown movie clips. So very short, like few-second clips, for instance, of maybe a clip from an episode of Seinfeld, a clip from Martin Luther King's I Had a Dream speech, maybe a tourism video from New York. And you won't see the videos, but you'll see the textual descriptions of them. And what you'll hear is actually this response, or what we call firing, of that individual brain cell in the hippocampus as he's experiencing these movie clips. And so what you'll hear is these pips, or these beeps, which actually represent when the cell, the neuron, is responding. And so what you'll see as he watches these video clips, the cell actually has a particular preference for one of the movies. So it'll take a few seconds for it to start. This is a Simpsons neuron. It's always interesting to... So I'll stop the video for a second. So obviously, the cell has a very specific response. It likes the Simpson video quite a bit. And the idea is that this cell is responding because it's actually forming a memory for this experience of seeing this particular funny clip from The Simpsons. Now what we're going to see is this patient actually freely recalling, right, remembering these particular video clips. So what you're going to hear this time is a distorted version of his voice, so he's just going to be saying what he remembers. And at the same time, you'll hear the firing, the response of this very same brain cell while he's actually remembering these events. telling, right? Did anybody notice anything special about when the cell fired? Before, right? It actually responded before he said anything. So not only was the cell responding when he first saw the video of The Simpsons, it actually came online as almost as if it was the thing that was responsible for his memory, and then he actually said, oh, The Simpsons, right? And then he laughs, right? So this part of the brain is not only important for forming these memories, but allowing us to recall them at a later point in time. And so we can ask, what would our life be like if we didn't have this part of the brain? What if we had no hippocampus? So what I'm going to show you now is actually a few minutes video of an interview with a patient who is actually missing this part of the brain on both sides, so in both hemispheres of his brain. And so what you'll notice about him, he's a very congenial man. He's known as EP in the literature. Friendly guy, very intelligent, right? He can do lots of things, copy drawings. You'll see him do some tasks on a computer. He'll even be able to tell you back things that happened like immediately before. But you'll notice something particularly peculiar about his behavior that kind of characterizes what happens when you lose this part of the brain.
We're starting our exploration of memory a few miles up the coast from La Jolla, with a man whose own ability to create memories vanished almost entirely a decade ago. Ever since, he's been helping researchers from the University of California, San Diego.
Hi, good to see you, by golly.
Today, Larry Squire and Jen Frascino are on the latest of many visits the team has made to the man known to memory researchers everywhere as EP.
Oh, it's wonderful. Got a nice sun for the camera.
Yeah.
A little work?
We're going to go in, we're going to do some work with that.
EP is now 82. In 1992, retired from a career in electronics, he suffered an acute virus infection that destroyed part of his brain.
Research and development, that's what I like.
Most of his thinking skills survived the damage virtually intact.
Why should people pay taxes?
To support your country and your counties and states to pay for things.
If you were lost in the forest during the day, how would you go about finding your way out?
I would find a river and follow the river down to wherever it may go. Ocean, lake.
EP can also copy complex drawings.
That is, huh?
And he not only has no difficulty repeating back a list of words, in this case, dog, raccoon, lion, and parrot.
Dog, raccoon, lion, and a parrot.
Good.
But he even has a little sly fun with Jen along the way.
What you got to add is about 2 more.
Oh, really?
Yeah,
Would that make it tougher?
And that would catch them. 7, you know. Leaf. Medicine.
EP really hits his stride when the testing of his cognitive skills involves Jen's laptop computer.
Gold. Having been in electronics over the years, I am amazed at all this. It's just wonderful. Believe me, little printed circuits, just, oh, you can't believe it. It used to be in a 6-foot rack, and down to this, it's just wonderful. When I was in electronics, this would be in a 6-foot rack.
But it's now that something odd about EP's behavior becomes apparent.
Printed circuits, diodes, triodes, and all that stuff in there. Oh, it's just amazing, believe me. When I was in electronics, this would be in a 6-foot rack. This would be in a 6-foot rack. It would be in a couple 6-foot racks. It would be in a 6-foot rack. This would be in a 6-foot rack. And now look at it, down to this. Little printed circuits. And
So he's not aware that he's told us 3 or 4 times that he used to be in electronics, that a computer used to fill a room, and that now it's down to the size of a microchip. He's just not aware that he's said those things several times.
No, he tells us the same stories again and again. We've heard these stories before, and we'll hear these stories again.
So he's obviously a very intelligent man. He knows facts. He can actually do a lot of complex tasks. But yet he's left with this profound ability, right, that once something leaves his mind, it's gone forever, right? To him, each time he tells Jen, the experimenter, that this has come down to a 6-foot rack, it's a new experience to him. And in fact, I haven't shown you the whole video, he's met Jen 200 or more times, and each time is new. He doesn't know who she is, won't know her name, can't recall her, right? So that he can remember things about that he used to be in electronics. He can tell you about probably where he grew up, many events from his childhood. Anything from the point that he has this virus infection on can't get stored in his brain, right? He's left with this profound, what's called anterograde amnesia. And so if we think about healthy memory, so somebody like you or I who has hopefully an intact set of hippocampi, we can consider, the amount of memory we can recall, right, as a function of our lifetimes. And so, obviously we're going to be able to remember things from the recent past more than we can from childhood, for instance. And that's very stereotypical, that memory has this kind of linear recall function. But this anterograde amnesia that these patients are left with, so when you have damage to these hippocampus, right, so this is actually a brain image from a patient like EP. And so this is called a coronal image. This is looking straight on somebody's head. And the structure, the hippocampus, is supposed to be right here and right here, but there's this big black space, right, that represents where this is missing. So patients who don't have these structures actually do fine at remembering their past, but from that time of injury on, nothing. Right? And that's what's known as anterograde amnesia. So, and what should be really apparent from this video of EP is that only this memory for events is actually impaired, and to some extent a little bit factual knowledge, but it's really specific to this event memory. Skills are intact, a lot of factual knowledge is intact, and habit and fear memories would also be intact in an individual like this. So it's really, this part of the brain is very specific for remembering the individual experiences that we have. And much of what we know, I have to give props to a patient known as HM. Until a few years ago, he passed away in 2008. His name is Henry Meliason. Much of what we know about how the brain subserves memories from the study of this one individual person. He's one of the most studied individuals in the history of all of psychological research. And he, like the patient we listened to the recordings from, had epilepsy that was not treated, able to be treated by medication. So in the 1950s, when he was in his 20s, a surgeon went in and took out both of these hippocampi, on both sides, to treat his epilepsy. No more seizures after that, or at least the seizures were controlled by medication, but he was left with profound amnesia. And until the surgeon did the surgery, we actually didn't know that that would happen. So he sacrificed quite a bit for us to know what this part of the brain does. And I just have a couple of quotes here to kind of illustrate what it must be like to be one of these individuals. So every day is alone in itself, whatever joy I've had and whatever sorrow I've had. Right now I'm wondering, have I done or said anything amiss? You see, at this moment, everything looks clear to me, but what happened just before? That's what worries me. It's like waking from a dream. I just don't remember. So he's very aware that he has this memory problem, but it's almost as if he's frozen in time, right? You can't evolve, right, from the time of this injury onward. You are who you are, and that's who you're going to be for the rest of your life. And so I think these words of HM himself give us a really profound implication of what memory does for us and how important it is for us to be able to record what happens to us moment to moment. And so one aside here is that one thing I want to point out is that early Alzheimer's disease actually looks a lot like one of these amnesic patients. So this is a brain scan from an early Alzheimer's disease patient. You can see they're missing these two hippocampi bilaterally on both sides, in both hemispheres. And so that's why the early stages of Alzheimer's disease looks a lot like this kind of dementia or anterograde amnesia. But the one thing that makes it different is that as the disease progresses, basically the whole brain is affected in Alzheimer's disease. So this is a healthy or non-Alzheimer's brain after death, and this is an Alzheimer's brain after death. You can see that there's a lot of what's called atrophy or cell death that happens just all over the place. So as the disease progresses, you get more than memory deficits, attention, social interaction problems. But at least at its onset, it looks a lot like these amnesic disorders. So I've shown you that the hippocampus is important for memory, but now we can think about what does it do exactly? What does it do that allows us to actually lay down these records of our experience? So we can think about a lay example, right? So imagine you're leaving your house for school or work, and you notice a new man leaving the house next door to you to walk his dog, and maybe that house is recently for sale. So you think to yourself, oh, that guy must be my new neighbor, right? And so this experience of seeing this guy with his dog walk down the street is going to activate a whole bunch of parts of our brain. Those involved in seeing, hearing, smelling, and even thinking, right, this thought of that he must be our new neighbor. So those brain regions don't directly talk to each other necessarily, right? But all of that information actually gets sent to the hippocampus, right? And so the hippocampus here is this kind of curvy structure in the middle. So it receives all this input representing the sights, sounds, smells, and semantic information of a given event, and it actually glues them all together, right? So it rapidly forms this memory representation that all of these things are related to one another and represents this particular experience, right? And it's because it's receiving this converging or all this input at the same time that it's able to do this gluing or this binding process. So we can also think about it in terms of remembering. So imagine, a few days later you notice a dog like walking down the street by himself, and you think, oh, that dog, he must be lost, right? And so again, seeing that dog is going to activate maybe the parts of your brain that are involved in perceiving, right, dogs. And then that information is then sent to the hippocampus. And that through being sent to the hippocampus, it then reactivates, right, that glued together representation of the first time you saw the dog. Right? And it allows you to actually retrieve, right? Oh, that dog must belong to my new neighbor because I've seen that dog together with that guy before, right? So this is like, right, the single cell that we listen to, the Simpsons neuron, being able to retrieve later point in time that when that guy recalled I'd seen that Simpsons video. Right? So this hippocampus is important for gluing together these memories, but also allowing us to reactivate or retrieve them at later points in time. But, to get to the essence of this talk, right, what the talk's about, I think we can think about what do we actually use memories for, right? It's nice that we can reflect on our past. That's, useful in some respects. But why I think our brains spend a lot of computational power doing this, right? A lot of things happen to us. Why do we have to actually remember them? And if we think about it, what we actually use our memories for is to help us do things in the present, right? So I can have expectations for what might happen to me. You guys can anticipate what I might say in the next few words. I can anticipate what you might ask me at the end of the lecture based on lectures I've given before, right? So I'm using my past knowledge to kind of make predictions about the near past, but I can also use them to project myself into the future, right? So I can imagine myself potentially a few weeks from now, a few years from now, and many years from now by using my memories, right? So we can develop goals this way and anticipate what might happen to us by using our memories. And so that's what I'm going to talk about for most of the rest of the talk. And so I think this is best illustrated obviously by a quote from Lewis Carroll, the White Queen, speaking to Alice, saying, "It's a poor sort of memory that works only backwards." So we can think back to, the TARDIS, right? Time machines allow us to travel backwards in time, but in this way, our time machine, the hippocampus, also allows us to travel forward in time. So I can ask you to think about something that's happening right now, but I can also ask you to think maybe back to a special birthday when you were a child, right? And you would use this part of your brain, right? The idea here is if I ask you to think about an upcoming birthday and what you might do, maybe you'd like to go dancing with your friends, right? You're actually using memories, right, to think about all sorts of things to derive that kind of anticipated experience. So this is who I'll be with because I know they've come to my past birthday parties and, I went dancing this year and last year and I really enjoyed it, so I'm going to go dancing this year, right? It's kind of this constructive process by which we use our memories. But we also use them to project ourselves into the very distant future. So if we're lucky enough, we might project ourselves to our 90th birthday when we're surrounded by our family, maybe our grandchildren, for instance, right? The idea is that this part of the brain is not only allowing us to reflect on our past, but build these representations of our futures. And so in essence, our brain is a prediction machine. And so I know this is going to be hard for you to see, so I'm going to read it to you. So we can look at this more directly, like scientifically. We can look at how, right, imagining is related to remembering, because projecting yourself into the future is an event of imagination. And so in this particular study, they just asked people to do imagery tasks. For instance, the cue here is imagine you are lying on a white sandy beach in a beautiful tropical bay. So somebody like you or I, again, who has their nice healthy brain, might say, It's very hot and the sun is beating down on me. The sand underneath me is almost unbearably hot. I can hear the sounds of small wavelets lapping on the beach. The sea is a gorgeous aquamarine color. Behind me is a row of palm trees, and I can hear the rustling every so often in the slight breeze. Now, I won't read it all, but you get this really vivid description of what's going on, a lot of detail, even some spatial layout, right? But what happens if you don't have the part of the brain that we know is important for memory, right? What if you had no hippocampus? Well, it turns out patients like EP and HM, they can't do these imagery tasks. They'll say something like, as for seeing, I can't really, apart from just sky. I can hear the sound of seagulls in the sea. I can feel the grains of sand beneath my fingers. I can hear one of those ships' hooters. And that's about it. And then the experimenter asks, are you actually seeing this in your mind's eye? No. The only thing I can see is blue. Right? So again, I won't read the whole thing, but the idea here is that they can kind of do the task, right? They're giving you things that make sense. But the image that they're telling us about is very degraded, right? It's not very detailed. It's not very spatially rich, right? And the idea is that because they don't have access to their memories, they can't recall what's happened to them, they actually can't use them to construct these future imagined scenarios, right? So this is really kind of profound in the sense that imagining, right, equals remembering. And so what I'd like to emphasize here is that memory and the way our brains store memory is not passive. Our job is not to veridically record all the experiences that we have. Memory is actually a very active and constructive process, right? We use our memories as building blocks, right, to potentially anticipate what might happen to the future. So here we're going back to our lovely dog example. So imagine now a couple weeks from now, you're running, taking a jog through the park, and this time you see the dog being walked by a new person, a woman. And again, this is going to activate a whole bunch of parts of your brain representing the sight, sounds, and smells, seeing this woman walking the dog. And that information is all sent to the hippocampus. But you've seen this dog before, right? And this new experience is going to share something, share some content with what's happened to you in your past. And that actually might allow you to not only form this new memory, but retrieve the old event, right? So while you're seeing this woman walking through the park with her dog, you actually are thinking about the previous time you've seen this dog. So that when you form a memory for the woman, right, so the idea is that this shared content, right, this shared dog allows you to trigger this old memory. And that when you form a memory for this new experience, you not only form a memory that the woman and the dog share some relationship, but you actually form a memory that links the woman and the man. So you've never seen these two people before, right? Yet your brain actually stores a representation that these people share some relationship, right? You might code that they're husband and wife, and that she lives in the house next door to you, even though you've never seen her anywhere in your neighborhood. And so in this way, memories for the past, right, influence the way we learn new things, but new things actually influence the way we remember the past. So there's this kind of constructive aspect and this push-play between what happens to us now and what's happened to us in the past. And so certainly remembering impacts the way in which we learn new things. And what's profound about this is that our memories go beyond our direct experience. We store things in our head that never happened to us. And we can talk about that at the end if you want. So this is something, I think anecdotally this all makes sense to us, but it's a pretty new idea that's become very popular in the last few years in neuroscience research. And so this is one of the things my lab actually looks at, this kind of constructive aspect of memory. And so how do we do that? Well, my lab studies people, and we actually stick them in big scanners, big magnetic resonance scanners, and we actually watch how their brains are active while they do all sorts of funny memory tasks. So this one that I'm going to describe to you today is very much like the man-dog, woman-dog example. So people come in, and they lie down in the scanner, and they see pairs of different stimuli, right? So here they might see a backpack and a horse at the same time. And they're just asked, okay, I want you to remember that the backpack goes with the horse because I'm going to ask you, right, that on a memory test. So we see many of these pairs of objects throughout the whole learning experience. But some of these actually are overlapping, right? So that you don't see the horse only once, you actually see it more than once. So this time, Maybe later on in the learning experience you see the horse. But now it's paired with something else, this lovely picture of a lake, right? And so in this task, what we ask people to do is we ask them, after they come out of the brain imaging machine, right, we ask them to do a memory test. And so we can ask them about things they directly learn. So here the cue is on the top, so I ask, okay, for the backpack, which one of these things was paired with the backpack? And of course the right answer is the horse. So it's a pretty easy task. But we also ask them for things that are indirectly related. So we can ask which scene goes with the backpack. And in this case, the answer is the lake because they both share a relationship with the horse. Right? And this is called an inference. Right? I can infer that the lake and the backpack are related because they share this relationship with a common item, the horse. So the idea here is that we're going to look at how brain activation during these learning experiences predicts how well people do on these various memory tests. So the idea is that if something is active while people are learning, they're actually forming these memories. And to the degree that they form these new memories, they're going to do better at these memory tasks. And so we can think about this, how remembering influences new learning more specifically. So if you look at the backpack horse, and then so the first time you see it, you're just learning to associate these two items. And then later on you see the horse now pictured with the lake. The idea is that you actually might think about the backpack, right? And that you actually remember what you saw before, and that you actually link it to the first event. So the lake is actually joined together not only with the horse, but with the backpack. And so that, maybe you see these more than once. So the same thing here, you see the horse, and this time you think of the lake. And so again, you're just reinforcing the relationship between the three different things, and that this goes across on several times, right? And the idea being that as you see these two interleaved relationships, that you actually learn to anticipate that the backpack and the lake go together. And if you do this, if you reactivate this kind of lake representation while you're learning the new things, it's actually going to make it easier for you to do this kind of very difficult inference test, right, later, right? So if I already know that the backpack and the lake go together, I'm going to really easily be able to answer that. So you might ask, well, how do we actually measure whether somebody's remembering the lake, right? I'm not going to ask them to tell me that, right? They're not going to be telling me anything while they're learning these things. And so we can actually do that. You can think of it as a kind of form of mind reading. So this is a complicated slide. So it turns out that why we use objects and scenes in this particular task is that our brains, different parts of our brains actually respond to these different kinds of things. So one part of your brain will be active when you're looking at objects. Another part of brain will be active while you're looking at scenes. And so you can kind of differentiate what people's brains look like when they're looking at these kind of items. And so the idea here is that here if I just represent a pattern, right? A picture, a snapshot of somebody's brain, and you can think of these gray and white pixels, right, as pixels in the image. So we can actually train a computer algorithm, like a computer, to actually say, okay, this is what this person's brain looks like when they're looking at scenes. This is what this person's brain looks like they're looking at objects. And so that this computer actually learns what the patterns of brain activation look like when people are actually viewing these items, right? And so we're going to then take this computer algorithm that we've trained, right, and apply it to this task that I've described to you. So we can give it an input image and say, okay, computer algorithm, based on what you've learned, is this person looking at a scene or are they looking at an object, right? So without them telling us, we can actually predict, right, what they're not only seeing, but what they're thinking about. And so we're going to do this in the context of this task. We're going to take one of these computer algorithms and ask what the person's thinking about when they're looking at the backpack of the horse, right, without them telling us. And so here we're looking for this reactivation of this lake scene and comparing it to some other trials where they're not thinking about scenes but thinking about objects. So that's what I'm going to show you here. So if I think about when I'm looking at the horse backpack the first time, right, I don't really reactivate the lake. I don't think about it because I don't know it goes with the horse in the backpack. But as I kind of interleave those two associations, the idea is, right, I start to activate, right, my representation of the lake, like my brain remembers seeing the lake before paired with the backpack, and that I join these things all together, right? So we actually can read out that the person's thinking about the lake while they're learning about the backpack and the horse, even though that they're not telling us that. So the big question is, does that have anything to do with memory, right? Can they, in doing that, they actually do better at these tasks? So does this amount that they're remembering the lake actually predict how well they're able to answer the relationship with the backpack and the lake? And yes, short answer. So this is actually a graph where each of these dots is a person in our experiment. And this here is how much they activate the lake. So higher values mean more lake. Right? And here is actually performance on these memory tests, these inferential memory tests. So more to the right means they're doing better. So the idea here is that the people who activate the lake the most do the best on this task, right? So the degree to which we can read out these brain responses, we can actually predict how well people can do these kind of flexible inferential judgments. So they're kind of combining these memories online in order to anticipate, right, that the backpack and the lake go together. And so we can also look at how the hippocampus, which I've been talking about a lot in this talk, so that we can see this is true. Here's the hippocampus, right? The more people also activate this hippocampal region during learning, the better they do at this task. So bigger values, better memory. And so what we think this means is that, right, hippocampus is allowing you to do better at these tasks, and it's because it's linking, right, the current experience to whatever you're thinking about, right? And so it's constructing memories for things that go beyond direct experience. So like our woman, man, dog example, right, it's actually forming online a representation that all of these things grow together, even though it never sees backpack and lake at the same time. So the last thing I'm going to talk about, just for a few slides on it, is sleep, right? Because it turns out, you know, we actually do important things during sleep. One of which is that we actually make our memory stronger. Right? And so one thing I haven't described to you about these particular brain cells in the hippocampus is that there's cells that are called place cells. They tend to respond not only to things like The Simpsons, but I'll have a particular cell in my hippocampus that responds when I'm standing here. Right? And if I move over here, I'll get a different cell, right, that fires reliably when I'm here. And those are called place cells. They maintain a map of our environment, right? And so what I'm showing you here is just kind of a diagram of what those place cells might look like in a rat's brain when he's traversing a maze. So here, this little gray thing is like my poor man's drawing of a rat, and that he's traversing this figure-8 maze. So first he goes on the blue arm, then he goes on the red, and he just keeps going back and forth and back and forth and back and forth. They do hundreds and thousands of these trials. So we can watch as Mr. Ratty goes along the maze, right? And he reaches different points in the maze. And each of these dots is meant to represent a location where we might see one of these hippocampal brain cells that responds, right? You'll get a specific cell that responds at the purple location, the blue location, the yellow location, the pink location, and so on, right? And we can see that here in this picture. So here's our lovely Ratty. And what I'm showing here, just pay attention to the bottom part. So these are cells 0 through 7. They're just labeled these numbers. And what we can see here is that they fire in sequence. So the purple cell fires before the blue cell before the yellow cell, pink cell, so on and so forth, brown cell, green cell, blue cell, orange cell. So these, you can see them firing, right, as the rat transverses the sequence while he's running, right? So you can actually see the rat's brain representing this particular spatial trajectory. What's really cool is that while the rat's sleeping, you see these same sets of cells fire in the same sequential order, right? As if it's replaying this experience of traversing the figure-8 while it's sleeping. And this is in particular a phase of sleep known as slow wave sleep or deep sleep. So experiences are definitely replayed while we sleep, and this has been shown in humans as well, not only lovely rats. But the question is, does it really make memory stronger? And so a group of scientists did a really clever study a couple years ago to test this idea. And so in this experiment, people learned object location, right, association. So they learned that this kitty goes in the bottom left-hand of the screen and this tea kettle goes in the top right. So while they're learning these object locations, they actually also hear the corresponding cells. So when they're seeing the kitty, right, they hear this meow, right? And when they see the tea kettle, right, they hear the whistle, right? And so they learn a bunch of these. And then the experimenters actually have them nap, right? And while they're napping, during this kind of slow wave sleep, they actually play half of the sounds, right? So they'll play meow while the person's napping, right? So the idea is they're trying to cue these memories while the person's sleeping to see how it's going to affect their memory on a spatial task. So after they nap, they get a test. So everything starts out in the middle. They take a mouse and they have to move the picture to where it goes, right? So it's a kind of spatial recall task. And you can measure people's error, like how close they get it to the exact position or not, and that's the behavioral measure in this case. And so the question is, for the ones that are kind of cued during sleep, are they going to do better at this spatial memory test? So one thing that's important to establish at first is that they learn the things equally in the first place. So they actually do the spatial memory test right after they learn them and right before they nap. So they're equal, things that are going to be cued during the nap and things that are not going to be cued during the nap, just as good. But what happens after the nap is that this is actually the change in error. And so you see less change, right, and this error for the ones that are actually cued during the nap. They actually start doing worse on the ones that weren't cued during the nap. So it actually works, right? Playing these sounds, right, for things that they learned while they're napping actually made their memories more durable, right? They made them last longer. So, great, right? Sleep is good, but what about lack of sleep? So let me ask the audience. So, all right, there's a lot of kids in the audience. I'm going to ask two different questions here. So for those people over the age of 20, how many of you actually get 7 hours of sleep a night? Not very many, right? There's very few. All right, for those kids under the age of 20, how many of you actually sleep 9 hours a night? Again, very few of you, right? So those are the recommended amounts of sleep for relatively those age groups. And you're not unlike the rest of the country. Right? For adults, 75% of the Americans sleep less than 8 hours a night, so we're all kind of constantly sleep deprived. And it's actually worse than that. 1 in 5 of us actually has a clinical sleep disorder as defined by the National Institutes of Health, right? Things like insomnia or sleep apnea, et cetera, right? So sleep is actually a pretty important kind of culturally relevant thing. We're all constantly sleep deprived. The question is, what impact does that have on our memories? Well, pretty profound, right? So in this study that I'll describe to you, people came into the lab, and like we do in my lab, they stick them into big scanners, and they measure their brain activation while they're doing memory tasks. So in this particular experiment, they might learn a list of words and have to do a memory test. So just kind of recognize whether they saw that word while they were in their scanner or not. And so one half of the subjects came in with a nice, good, 8-hour night's sleep, right? And then they they learn the new things and they do the memory test. And another group, sleep deprived, right? No sleep the night before. And so what I'm showing you here is a comparison in brain activation for the sleep group compared to the no sleep group. And it turns out the people who sleep the full night actually use this part of the brain we talk about a lot, the hippocampus, more than the people in the no sleep group. So, right, sleep group, you use this important memory structure more. You're more able to engage it while you're learning new things. And that had a functional consequence because the people in the no sleep group did a lot worse than the memory test. They actually weren't able to form these new memories. So sleep playing our memories during sleep helps us strengthen memories, but not sleeping will make it really hard for us to learn new things. So what does all of this mean? So one thing I want you to take away from this lecture is that soap opera amnesia is not real. And for those fans of True Blood, right, this is most recently observed by Eric Northman, who completely forgets everything that happened to him, but yet can form all these new memories. That actually doesn't happen as a result of brain damage, only maybe magic, or in some cases some rare forms of psychosis will do this. But this type of soap opera amnesia doesn't really happen. Really what amnesia is this kind of anterograde amnesia that I described to you. And you laugh, but these are actually pretty accurate pop cultural depictions of this disorder. So Dory and Finding Nemo is a really good depiction of what an amnestic is like, as is Leonard Shelby in the movie Memento, right? So if you want to, I recommend those movies because they're pretty good for describing this particular syndrome. But more seriously, what I hope you take away from this is that you realize that memory is a many-varied thing. It's not just one thing, and we can't define it in just one way. And that what really we're doing with our memories is actively constructing experience, right? We are anticipating what might happen to us a few minutes from now and also years from now. And that because of this kind of active constructive process, what we store as memories actually go beyond direct experience and may reflect things that never happened to us. And for this reason, it's ever changing, right? What's happening to me now is influencing my memories for the past, and my memories for the past is influencing the way I'm forming a memory for this particular event, like speaking to you now. And finally, I hope I've hammered in the importance of sleep, because our memories do like to sleep. We need sleep to learn. Sleep helps us store the things we learn. And I think this has important implications for just our basic understanding of how the brain supports the mind, but also for educational practice. So understanding this push-pull between coming into a classroom and understanding that our existing knowledge influences the way we learn new things, but also understanding these more practical things about how sleep, right, influences the learning environment. And hopefully by understanding these mechanisms, right, understanding how the hippocampus works and how it actually anticipates the future, we might be able to develop interventions that can improve function in clinical populations, maybe enhance memory and aging, or potentially help neuropsychiatric disorders like depression, where people are more likely to overgeneralize. They take their experience for the past and are more likely to think that it's going to happen in the future, right? So we want to stop them from doing that as well. I think this has a lot of, this kind of basic science has a lot of practical cultural significance as well. So with that, I'll thank you guys.
Dr. Preston will be happy to answer questions. So raise your hand if you have a question. Can you see? Go ahead.
Yeah, go ahead. You got it in the red back there. Oh, okay. So the storage process, I don't know that we know exactly, right, that it's probably pretty intricate and goes down to the molecular level, right? So there's a whole cascade of things that allow memories to be distorted. And that would be a whole another lecture, right? I'll kind of address more the latter point, this idea that there might be these people with superior autobiographical memory. Now, that's exceedingly rare, right? And there have been a few kind of confirmed and documented cases. There was actually a piece about this in 60 Minutes right before last Christmas. Did any of you guys see it? Yeah, a few of you, right? So a group of researchers at the University of California, Irvine, is looking at these people specifically. And these are people who remember every day of their life in exquisite detail. And they can confirm this by asking them like what the weather was like or what events they went to on that day. So they can get confirmation for these memories. We don't really know what's going on in those people's brains yet. They've just been started to be studied in the last 5 or 10 years, and they're just starting to take brain scans from them. And so I don't know, but it's incredibly fascinating. One idea is it's not about how the hippocampus works, but how the hippocampus interacts with other parts of our brain that kind of control things. So it's about the ability to control our recall process so we can go in there and grab the right thing. Which maybe some of us can't do very well. Maybe it's in there, but we just can't access it in the right way. So it might be this interaction between our memory storage processes as well as kind of more top-down, like how I can get to those memories in the first place. But I don't know. That's a good question. Fascinating. Yeah? For sure, right? Yeah, sorry. She asked if insomnia actually impairs memory, and I would say yes, and that it's an extreme form of sleep deprivation that's going to accrue over time. Yes, the worse and worse your memories are going to get, for sure. I'm going to try to spread myself out. Go ahead. Yeah, you. No, that doesn't work. That does not work. Yes? No. So I should kind of describe, I took it out, but I will say this. Brain imaging, what's called functional magnetic resonance imaging, is a very indirect measure of neural activity. So we're not measuring the response of a single neuron or even the response of 50 neurons. We're listening to tens of thousands of neurons, and we're not even listening to their spike rate. We're actually listening to blood flow changes that happen, right, as a function of neural activity. So when a neuron is active, it requires all this energy to do what it's doing. Our bodies compensate by sending a lot of blood rushing to our head, and functional magnetic resonance imaging measures those changes in blood flow that happen as a function of this energy needs. It's a good question. Yeah? I would think so, right? Because I think anytime you're constructing anything, right, you're probably using your knowledge. And you might be doing this kind of creative aspect, right? You take some things and you might form this novel link to something else and generate this new idea. So for sure, right, you're probably using these hippocampal regions to do these kind of things. Uh-huh. Back there, in the orange. So I'm not going to be able to quote you the exact numbers, but definitely in the teenage years, right, adolescence is about 9-10 hours, right, on average, which all of you teenagers out there are seriously sleep deprived. I know this for sure. For adults, it actually tapers off as you get older. So, for the average adult, kind of middle age, it's about 7 hours, and older adults tend to sleep even less than that. But you should be sleeping at least 9 hours a night. Yeah.
What about naps?
Naps are good.
Does it have to be like all at once sleep, or can you sleep like 4 hours?
No. So for regular sleep, you do need to sleep all at one time for night sleep. There also is a benefit to naps, and there's a whole body of research looking at how napping improves memory function, but that's on top of the sleep that you're already having at night. So the idea is that if you learn something new, you might want to go take a nap for like 20 minutes. Right? And that actually, I'm serious, it can help you. People have done these studies, right? So that you actually, whatever you happen right before that, you're going to remember it better. Yeah. Up there. At least at its beginning, right? So the very first part of the brain that's stereotypically affected in Alzheimer's disease is the hippocampus. You start to see these plaques and tangles, which are the stereotypical signs of Alzheimer's disease in this part of the brain first, which leads to cell death, right? But as the disease progresses, and it progresses very rapidly, those plaques and tangles go everywhere and affect almost every part of the brain. And so you get devastating kind of cognitive disorders of all sorts beyond memory. But the first thing you see in one of these patients is memory deficits or navigation. Anybody want to hazard a guess why navigation? Place cells, right? Like place cells, right? The part of the hippocampus is coding, making these maps of place cells. And so these patients will also, if early Alzheimer's, will also have problems navigating routes, right? They'll forget how to get from one place to another. Way up there. The sleep. So this kind of brings up two questions. The sleep is important, but you kind of allude to something that's known as mass versus space practice, right? So imagine you're trying to pull an all-nighter before an exam, right, so you can remember everything that you need to. You might do pretty well in the exam, despite your sleep deprivation, but you will not remember any of that stuff ever past that exam. Right? So it depends on what your goal is, but if you're truly a student who wants to learn stuff, take the extra hour sleep. Yeah. Yeah. Mm-hmm. Yeah, yeah. Yes, yes. So, for instance, skills, right? So being able to do these motor tasks, like learning how to ride a bike, or doing something simple like tracing something in a mirror. So imagine you can't see your hand. All you can see is a mirror representation of your hand, and you have to learn how to trace figures in it, right? It's a very commonly used experimental task, and it's harder than it seems. So it turns out if you're damaged a part of the brain known as the basal ganglia, which is, again, a set of nuclei and structures pretty much embedded right in the center of your brain. It's the part of the brain that's damaged in Parkinson's disease or Huntington's disease. Those patients have a lot of trouble acquiring new skills. Right? So other things like fear memories, those are supported by a part of the brain called the amygdala, right, which is very important for emotional processing. So you do see the same kind of localization that you see with this kind of event memory that I talked about. Right? And that's all, most of what we know is about study of all these different kind of neurological disorders that allow us to tease apart what's essential for one form of memory versus another. Pink shirt in the middle. So it's really, it kind of gets choked out by these like plaques and tangles which start taking up all like the metabolic or the energy resources, right? And basically the cells don't start to die because they're not being fed as much, or they are not being used in the same way. So you see this kind of cell death, right? That leads to basically a huge lesion, like if I went and scooped it out of there with a spoon, right? Which is basically what neurosurgeons do. All right. You there, that everybody's pointing at. Yes, yes.
Why are we able to remember something not others?
Good question. I think that's a bigger question than you mean it to be. So I think that's something that I'm very interested in, because obviously things that are really important to us, maybe they're involved with a particularly emotionally arousing event, those kind of things are more likely to be remembered, right? You form more lasting memories for those kind of things. Things that you need to do to achieve your goals, right? Or you're motivated by, right? You might be really motivated to learn how to play a video game, so you're going to learn that particular thing really well and the rules are behind it. But maybe you aren't so motivated to learn, right, your organic chemistry, right? You can see, and that's clear because you devote attentional resources to forming these memories, but there's also maybe biological things that you do, right? You get all these neurotransmitters, these chemicals, right, that are poured all out through your brain when you're emotionally aroused, or when you're really motivated. There's a neurochemical called dopamine, right, that your brain releases, and that chemical dopamine actually goes to the hippocampus. So when I'm really motivated, I'm making my hippocampus work harder, maybe work better, so I'm more likely to form memories. So it's a really interesting question, but there's probably a lot of things, right? And we don't quite understand it all. Up there, blue shirt, black watch.
We know the difference in the brain between when you're remembering past events and you know it's past events versus when you're imagining something in the future and you know you're doing that. You're using the materials of memory, but
So there are some subtle differences. They're not as subtle as you think. So sometimes you activate the hippocampus even more when you're imagining the future than when you're retrieving the past. Parts of the frontal lobe, right, in the front of your brain are also more active when you're imagining the future. So there are some differences. Maybe the follow-up question to that somebody might ask me is, how do I tell the difference between something that I know is true and a memory that I have that may not be true, right? Which is kind of a little bit the same thing. So how do I tell the difference between, how do I know my brain's right? You don't, right? What our brains actually store are subjective experiences and not reality, right? And most of us will endorse, I can be absolutely certain something happened to me in this particular way, and this person was there, and it happened at this time, and I was wearing this shirt. You might be right for the most salient of those events, right? but a lot of the stuff you're probably not going to be right at, even though you swear on your mother's grave that it's true. Our brains record our subjective reality and not the objective truth, right? And that has a lot of implications for law and neuroscience and lots of other things.
So, Alison,
Yeah.
we've got a bunch of questions here from the webcast audience.
Yeah.
I'm going to read one for you. It comes from Julie, and she asks, could you elaborate on the fact that we remember things that have never happened to us?
Yeah, so certainly. So imagine, I can talk about this man, woman, dog example. So right, imagine I see this dog, right, being walked by the woman in the park, and my brain says, oh, that woman goes with the dog, and they're husband and wife, and she lives in the house next door to me, right? I store a memory for that. Maybe she's not the guy's wife, right? She's actually his dog walker. She doesn't live next door to you, but you swear to God, and you actually go and tell your mother or your spouse that, oh, I saw the woman who lives next door to us, right? You can easily, through this memory construction process, kind of form these things that beyond our direct experience and be absolutely certain that, well, why do you think she lived next door to us? Because I saw them together at some point in time, right? It's through this aspect of construction that we can form things beyond our direct experience, right? We form these false memories. And you can kind of think about it, I've kind of posed it to you as a very positive thing, right? That this kind of constructive, adaptive process allows us to anticipate things in the future, right? I can do better at these difficult inference tasks. But there's a cost, right? Sometimes I'm going to get things in there that may not be true. Right? And so, through this kind of ever-changing memory, we can distort, right, reality. But it's the same kind of neurobiological mechanisms that would do this. Go ahead. That is a really good question, and we don't know the answer to that, right? It's a really good question. Exactly. We don't know, right? And it's actually something that's really important to understand, but we really don't know. So do you have a memory for a man dog and a woman dog, and that somehow those things are represented truly and then linked? Or do I really lump the woman together with the man and the dog and don't remember I saw her in the park, in fact, right? We don't really know. And you actually could have both. Right? And we really don't know, but it's a really kind of insightful question. Yeah, please, sure. So working memory is, I'll define it for those who don't know. Working memory is kind of the things that we're operating on right here and now. So it's the kind of things that are going on in my head, right? So stereotypically we think of this as like if I give you a 7-digit or a 10-digit phone number, you might rehearse it, right, in your mind in order to remember it. That's called working memory or immediate memory. So usually working memory is impaired by damage to different parts of the brain, most notably the frontal lobes. And to improve it, I think it's hard. Lots of people are trying to do it with like training exercises. They're trying to train your brains to do better, to kind of be able to work on more things at once. I think there is kind of a limit to how much we can keep in our mind at the same time. I think if you think about multitasking, right, how many things can you actually work on at the same time? It's pretty tough. So you might be able to push yourself a little bit, right, beyond your natural limits, but probably not very far. But maybe somebody will come up with some genius idea about how to do that. I don't know. Way up in the back. I actually don't know that work. I think in some cases that's true. Right? For some things it might be true. Certainly our brains are doing a lot of stuff that we're not typically aware of. So, right, in this case, I showed you, like we look back to our Simpsons neuron, right? It's doing a lot of stuff before I actually verbally respond to you. And it actually may be firing before I'm actually conscious of having that memory event. So there are certainly many cases where that might be. And that's certainly the case for a lot of these tasks, a lot of skill tasks we don't even think about, right? If I ask any of you to describe to me exactly how to drive a car, you're going to have a lot of trouble verbalizing that and visualizing the steps. You can do it, but it takes effort. And so for a lot of those things, your brain is on autopilot, right? And there's a threshold which you're making decisions about how much to push down that accelerator pedal without even being conscious of it. So certainly there are some things for which that is very, very true. Yeah. Up there, a white shirt.
What is deja vu?
I always get that question. Again, I don't think we know for sure, but I'll speculate. It could be, right, that something that's happening in your current environment triggers enough that's similar to an existing memory to make you think, right, that this experience has happened to me before, right? So it's some pattern of activation across your brain that, right, cues this subjective sense of, wow, I've been here, done this, heard this before, right? So it's probably related to kind of these patterns of activation that lead to this really subjective confidence, right? But may not be true, right? Because again, our subjective confidence in our memories is very much detached from what is actually true, right? And so I imagine deja vu is something a bit like that.
So one more question for Dr. Preston. Go ahead.
Purple.
How exactly how does the brain sort information? And what I mean by that is, like, if in the example that you were giving where you saw then the woman with the same dog that you saw, how does your brain take that dog and recognize that it was from another memory? And then if you then asked or told me the word dog, would I think of that dog many other dogs I've seen, all from various events in the life?
So with the event memory, I think a lot of things will depend on how you sort it, right? So one thing that's going to be especially salient to you is, for us, we're very visual species, and space and place is very salient for our brains. Our brains code it very well. So a lot of times, if I'm in the same spatial environment and something similar happens, right, that's going to kind of sort that memory in a similar way. Whereas if this happens at a different kind of place and a different time, I'm going to sort that differently. So there are probably a lot of factors that influence what things are treated like and what things are treated different. For things like category information, that's, again, a whole other talk and a whole other line of research. So there's some ideas that when you think about dogs, right, you activate lots of mental representations of dogs. You might also activate cat, right, because it's semantically related, or, right, bones, or distantly veterinarians, right? You have this kind of connected set of information about all these semantically related things, that some things are really strongly semantically related. So when I think about dog, I also strongly activate cat and maybe a little bit veterinarian, right? And so that, your brain's kind of sorts this information based on its semantic relatedness and experience, right? That doesn't mean it's necessarily stored,